Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on redox reactions, and our first topic of interest is disproportionation reactions. A disproportionation reaction is a specific type of redox reaction in which one element is both oxidized and reduced, and it forms at least two products where the element appears in different oxidation states. These reactions are unique because they combine the principles of electron loss and electron gain into a single process involving the same element. So for example, let's consider the disproportionation reaction of nitrogen dioxide and water. We're going to go ahead and look at every compound and assign oxidation numbers to begin with. Here we have nitrogen dioxide. Oxygen is going to have an oxidation number of -2, and there are two oxygen atoms. This gives us a total negative charge equal to -4. This is a neutral compound, so that means we have to make sure that the sum of the oxidation numbers equals 0. For that to be true, nitrogen has to have an oxidation number of +4. +4 minus 4 equals 0. Next, we have water. Oxygen here again has an oxidation number of -2. Hydrogen has an oxidation number of +1. That's the rule for hydrogen when it is bonded to nonmetals. And there are two hydrogen atoms, so this gives us a total of +2. +2 minus 2 equals 0, which is exactly what we want for a neutral compound, which water is. Next up, in the products, we have nitric acid. Here, oxygen once again has an oxidation number of -2, and there are 3 oxygen atoms. This gives us a total negative charge equal to -6. Hydrogen has an oxidation number of +1. It's bonded to nonmetals. And here, once again, nitric acid is a neutral compound. It's a neutral acid, so that means the sum of the oxidation numbers needs to equal 0. What we have here is +1 minus 6. That gives us a total of -5. To ensure that sums up to 0, nitrogen needs to have an oxidation number of +5. +1 plus 5, that's equal to +6. +6 minus 6 equals 0. Now last, we have nitrogen monoxide. Oxygen once again has an oxidation number of -2. Nitrogen is going to have an oxidation number of +2. Their sum equals 0, and that's exactly what we want since nitrogen monoxide is neutral. Now, taking a look at everything we've solved here, our nitrogen in the reactant side has an oxidation number of +4. In the product, nitric acid, nitrogen has an oxidation number of +5. Simultaneously, in the product, nitrogen monoxide, nitrogen has an oxidation number of +2. So if we compare +4 to +5, we notice that we're increasing the oxidation number, which means we're losing electrons, and that is oxidation. Now, also looking at nitrogen in the reactants and comparing it to the nitrogen in nitrogen monoxide, we're going from +4 to +2. So there's a decrease in oxidation number, which means we're gaining electrons. So nitrogen is reduced. What we're seeing is that the nitrogen in nitrogen dioxide undergoes both oxidation and reduction, and that showcases the defining feature of disproportionation reactions. With that, we can move into our next topic, which is learning how to balance redox reactions. Before we really start this section, let's review how to generally balance chemical reactions. The first step involves identifying the reaction. You start by determining the reactants, the products, and their physical states. Then you can go ahead and summarize the reaction in its basic form, including all of the species involved. So you're essentially writing the unbalanced equation. Then you can begin to balance one atom at a time. Begin with the element that appears in the most complex substance. And here you can use fractional coefficients if needed to simplify the process. But then by the fourth step, you want to adjust the coefficients to whole numbers. So if fractional coefficients are present, you're going to multiply all the coefficients by a factor that ensures they are whole numbers. And then your last and final step is to confirm that the number of atoms for each element and the total mass are conserved on both sides of the equation. These steps focus on ensuring that the law of conservation of mass is upheld. However, when it comes to oxidation-reduction reactions, balancing becomes a little bit more intricate due to the need to account for both mass and charge. So again, in redox reactions, we're not just balancing the number of atoms. We also have to balance the electron transfer between the species being oxidized and being reduced. This means ensuring that 1, the number of electrons lost in oxidation equals the number of electrons gained in reduction, and 2, both the net charge and the number of atoms are balanced on both sides of the equation. To accomplish this, we use a systematic approach known as the half reaction method. This method divides the reaction into 2 parts, the oxidation process and the reduction process, so that each can be balanced individually before then combining them together into the final balanced equation. So let's go ahead and go over the step-by-step breakdown of the process before we tackle a couple of practice problems. First, we're going to assign oxidation numbers. We want to identify the oxidation states of all of the elements in the unbalanced equation, and then determine which species are oxidized and which species are reduced. Once we know that, we can move into the second step, where we want to write separate half reactions. We're going to have an oxidation half reaction and a reduction half reaction. Once that's written, we can move into balancing all of the elements in each half reaction, except for hydrogen and oxygen. Once all of those atoms are balanced, then we can concern ourselves with balancing oxygen and hydrogen. To do that in acidic solutions, you're going to add water to balance the oxygen, and you're going to add hydrogen ions to balance hydrogen. After that's done, we then want to balance charge. To do that, we're going to add electrons to one side of the half reaction to equalize the charge on both sides. Then we want to equalize electron transfer. To do that, we will multiply the half reactions by appropriate coefficients so that the number of electrons lost in oxidation equals the number gained in reduction. Next, we can combine the half reactions. We will add the 2 reactions together, ensuring that electrons cancel out, and we're going to combine reactants and products into a single balanced equation. Now, if the redox reaction occurs in acidic solution, then we're done. We can just do a quick verification and that's it. But if it occurs in basic solution, then we need to add enough hydroxide ions to both sides of the equation to convert hydrogen ions to water. And here we may need to cancel some water molecules after doing this. And then our final quick check is that the charge on both sides of the reaction arrow are the same. Now, this might be a little confusing, but it's going to be okay because we're going to do two practice problems, one in acidic solution and one in basic solution. Let's start with this example problem. Balance the following redox reaction that occurs in acidic solution. In this reaction, we have tetraphosphorus reacting with nitric acid to form phosphoric acid and nitrogen monoxide. Let's begin with step 1, where we need to assign oxidation numbers. We're going to assign oxidation states to all of the elements in this unbalanced equation. Now, what we have here is tetraphosphorus. This is in its elemental form, so the oxidation number is 0. In nitric acid, we have oxygen, which has an oxidation number of -2. And there are 3 oxygens, which gives us a total negative charge of -6. Hydrogen has an oxidation number of +1 when it's bonded to nonmetals, and nitrogen here is going to have an oxidation number of +5. Here we have +1 +5, which gives us a total of +6. +6 minus 6 equals 0, which is exactly what we want because nitric acid is a neutral acid. Then in the product side, we have phosphoric acid. Oxygen here has an oxidation number of -2, and we have a total of 4 oxygen atoms. This gives us a total negative charge of -8. Hydrogen has an oxidation number of +1, and there are 3 hydrogen atoms. So we have a total of +3. To ensure that the sum of the oxidation numbers equals 0, we have to assign phosphorus an oxidation number of +5. So now we have +3 + 5 gives us a total of +8. +8 minus 8 equals 0. Then we also have nitrogen monoxide in the product. Oxygen has an oxidation number of -2, and nitrogen +2 + 2 minus 2 equals 0. Now let's identify what's oxidized and what's reduced. Looking at phosphorus, here on the reactant side, it has an oxidation number of 0, and it appears again in the products in phosphoric acid where it has an oxidation number of +5. Going from 0 to +5, that's an increase in the oxidation number, which means that phosphorus is losing electrons and it is oxidized. Nitrogen, on the other hand, has an oxidation number of +5 on the reactant side. It reappears in the products as nitrogen monoxide, and it has an oxidation number of +2. Going from +5 to +2, that's a decrease in the oxidation number, which means it's gaining electrons and it's reduced. So to summarize here, phosphorus is being oxidized in this reaction and nitrogen is being reduced. So the next step is to then write the half reaction. We need to separate the overall reaction into 2 half reactions. We're going to have our oxidation half reaction and our reduction half reaction. In our oxidation half reaction, we only include the substances containing phosphorus because that's the element that's being oxidized. So on the reactant side, we have tetraphosphorus, and on the product side, we have phosphoric acid. In a similar way, the reduction half reaction only includes the substances containing nitrogen because nitrogen is the element that's being reduced. So on the reactant side, we have nitric acid, and on the product side, we have nitrogen monoxide. Now that step 2 is complete, we can move into step 3, where we're going to balance each of the half reactions. To do that, we first balance all of the atoms except for hydrogen and oxygen. Once that's done, then we can balance oxygen by adding water as needed, and we can balance hydrogen by adding H+ as needed. Let's begin by balancing the atoms in the oxidation half reaction. We're going to start with phosphorus. We have 4 phosphorus atoms on the reactant side and only 1 on the product side. So to balance that, we're going to add a coefficient of 4 in front of phosphoric acid. Now that's balanced, and we can worry about oxygen next. We're going to balance oxygen by adding water as needed. Now on the product side, we actually have 16 oxygen atoms. To balance that, we're going to add 16 water molecules on the reactant side. Now both sides have 16 oxygens. Our final step is to balance hydrogen by adding H+ as needed. So on the reactant side, we have 32 hydrogens, and on the product side, we only have 12 hydrogens. To balance this, we're going to add 20 H+ to the product side, and now both sides are completely balanced. Now that the oxidation half reaction is good to go, we want to next balance the atoms in the reduction half reaction following the same exact steps. We're going to start by balancing nitrogen. There's 1 nitrogen atom on the reactant side and 1 nitrogen atom on the product side. So nitrogen is all good and balanced. The next step is to balance oxygen by adding water as needed. On the reactant side, we have 3 oxygen atoms, and on the product side, we only have 1. So to balance this, we're going to add 2 water molecules to the product side, and now both sides have 3 oxygen atoms. Finally, we're going to balance hydrogen by adding H+ as needed. On the reactant side, we have 1 hydrogen, and on the product side, we have 4 hydrogens. So to balance this, we're going to add 3 H+ to the reactant side, and now both sides have 4 hydrogens. In fact, everything is balanced in our reduction half reaction. Step 3 is now complete, and we can move into step 4. In step 4, we want to balance each half reaction with respect to charge by adding electrons to the more positive side. So I'm going to go ahead and erase some of this extra work so we can figure out how to appropriately do this. Let's start by looking at our oxidation half reaction. The oxidation half reaction is neutral on the reactant side, but it carries a +20 charge on the product side. The charge can be balanced by adding 20 electrons to the product side. What about our reduction half reaction? The reduction half reaction has a +3 charge on the reactant side and a neutral charge on the product side. So to balance this, 3 electrons can be added to the reactant side. Now we need to do a quick check. The change in oxidation state must equal the number of electrons transferred in each half reaction. And we want to do this quick check because it serves as a sanity check that the 2 half reactions have indeed been balanced correctly. Now we can start by looking at our oxidation half reaction. In the oxidation half reaction, each phosphorus atom changes from an oxidation state of 0 to an oxidation state of +5. So that means each phosphorus atom loses 5 electrons, and there's a total of 4 phosphorus atoms in the half reaction. So 4 times 5 is equal to 20 electrons, and that matches the number of electrons we've added in to our balanced equation. So far, so good. What about in the reduction half reaction? In the reduction half reaction, the oxidation state of nitrogen changes from +5 to +2. Therefore, the nitrogen atom gains 3 electrons, which is the same as the number of electrons in the reduction half reaction. So this quick check gives us confidence that the two half reactions have been correctly balanced for both atoms and for charge. And now we can go ahead and move into our 5th step. Here we want to multiply the two half reactions by factors that equalize the number of electrons. In our oxidation half reaction, we have 20 electrons. In our reduction half reaction, we have 3 electrons. The least common multiple of 20 and 3 is 60, which means that we're going to go ahead and multiply our oxidation half reaction by 3. And we're going to multiply our reduction half reaction by 20. For our oxidation half reaction, this gives us 3 tetraphosphorus plus 48 water molecules on the reactant side. And then on the product side, we have 12 phosphoric acid plus 60 H plus 60 electrons. For our reduction half reaction, we have 20 in front of nitric acid plus 60 H plus 60 electrons. This is all on the reactant side. On the product side, we have 20 in front of nitrogen monoxide plus 40 water. And these versions of our oxidation and reduction half reactions is what we're working with as we move into step 6. In step 6, we're going to be adding the two half reactions. Anything that occurs on both the reactant and product sides will cancel out. Therefore, the 60 electrons cancel out, and the 60H plus also cancel out on both sides. In addition, there are 48 water molecules on the reactant side and 40 water molecules on the product side. This leaves us a total of 8 water molecules on the reactant side in the final equation. So if we go ahead and add these up, what we get is 3 in front of tetraphosphorus plus 8 water molecules plus 20 in front of nitric acid. And that's all on the reactant side. On the product side, we have 12 in front of phosphoric acid plus 20 in front of nitrogen monoxide. Now, since this reaction occurs in acidic solution, we have completed the process of balancing the equation. If it had occurred in basic solution, we would have an additional step, and that's going to be illustrated in the next practice problem we're going to do together. But for now, we have completed this practice problem, and you can do one final check to verify that the charge on both sides of the reaction arrow is the same. So we can quickly do that. Most of the time, if a mistake has been made, the charge on the reactant side will not equal the charge on the product side. For this reaction, both the reactant and product sides are overall neutral. Therefore, we have a high degree of confidence that the equation was in fact balanced correctly. Beautiful. Now let's move on to our next example. This one says, balance the following redox reaction that occurs in basic solution. Here we have permanganate ion reacting with bromide ion to form manganese 4 oxide and the bromate ion. Notice that this reaction occurs in basic solution, so we're going to repeat the steps that we just followed in the previous practice problem. Once we've completed all those steps, we're just going to add enough hydroxide ions to both sides of the equation to convert H plus to water. Now let's go ahead and get started with step number 1. Here we're going to assign oxidation states to all of the elements in the unbalanced equation. And then we're going to use the oxidation states to identify the substances being oxidized and reduced. In the permanganate ion, oxygen has an oxidation state of -2, and there are 4 oxygen atoms, so we have a total negative charge that's equal to -8. Now, the total charge for the permanganate ion is -1. So in order to ensure that the sum of the oxidation states add up to -1, manganese needs to have an oxidation number of +7. +7 minus 8 gives us -1, which matches the charge for this ion. Perfect. Next up, we have the bromide ion. It has an oxidation number equal to its ionic charge, so -1. Now we can worry about the products. So here we have manganese 4 oxide. This is a neutral compound. Oxygen has an oxidation number of -2, and there are 2 oxygen atoms. So this gives us a total negative charge of -4. In order for the sum to equal 0, manganese needs to have an oxidation number of +4. And then last, we have our bromate ion. This has a charge of -1, so we have to keep that in mind when we're summing up our oxidation numbers. Here, oxygen is more electronegative, so it has its typical oxidation number of -2, and there are 3 oxygen atoms. This gives us a total of -6. In order for the sum to equal -1, bromine has to have an oxidation number of +5. Now, if we take a closer look at bromine here in the reactants and here in the products, we notice the oxidation number goes from -1 to +5. So it increases in the oxidation number, which means it loses electrons and it's oxidized. On the other hand, if we focus on manganese, here in the reactant side, it has an oxidation number of +7, and it goes to +4 where it appears in the product side. So here our oxidation number is decreasing, which means it's gaining electrons and it's being reduced. So we now know bromine is oxidized and manganese is reduced. And that helps us move into step 2, where we want to separate the overall reaction into 2 half reactions, our oxidation half reaction and our reduction half reaction. For our oxidation half reaction, we're going to have our bromide ion on the reactant side, and we're going to have our bromate ion on the product side. For our reduction half reaction, we are going to have our permanganate ion on the reactant side, and then we're going to have manganese 2 oxide on the product side. With that, we can move into step 3. We want to balance the half reactions by first balancing all of the atoms except for oxygen and hydrogen After those atoms are balanced, then we can concern ourselves with balancing oxygen by adding water as needed, and balancing hydrogen by adding H plus as needed. Let's start with balancing our oxidation half reaction. Here we have one bromine atom on the reactant side and one on the product side. So that is already balanced. Now we can move into balancing oxygen by adding water as needed. On the reactant side, we have no oxygen atoms, and on the product side, we have 3. So to balance that, we're going to add 3 water molecules to the reactant side. Finally, we want to balance hydrogen by adding H plus as needed. On the reactant side, we have 6 hydrogen atoms and none on the product side. So to balance that, we're going to add 6 H plus to the product side. Now our oxidation half reaction is balanced, and we can move into our reduction half reaction. On the reactant side, we have 1 manganese atom. And on the product side, we also have 1 manganese atom. So that is already balanced. We can move into balancing oxygen next. To balance oxygen, we add water as needed. On the reactant side, we have 4 oxygen atoms. On the product side, we only have 2. So to balance that, we're going to add 2 water molecules to the product side. Finally, we need to balance hydrogen by adding H plus as needed. On the reactant side, we have no hydrogen atoms. On the product side, we have 4. So to balance that, we're going to add 4 H plus to the reactant side. Now, we've balanced the atoms in both of our half reactions. We can move into step 4. In step 4, we want to balance each half reaction with respect to charge by adding electrons to the more positive side. Looking at our oxidation half reaction, our reactant side has a charge of -1, and our product side has a charge of +5. In order to balance that, we're going to have to add 6 electrons to the product side. Now both sides have a total charge of -1. Let's do our reduction half reaction. On the reactant side, we have a total charge of 3+. On the product side, it's completely neutral. So to make sure both sides are balanced, we're going to add 3 electrons to the reactant side. This way, the charge on the reactant side is 0, and the charge on the product side are 0, and they match. From here, we want to do a quick check and ask, does the change in oxidation state equal the number of electrons transferred? For our oxidation half reaction, the oxidation state of bromine changes from -1 to +5. This corresponds to losing 6 electrons, so we did that correctly. Now, for our reduction half reaction, the oxidation state of manganese changes from +7 to +4, and that corresponds to gaining 3 electrons, which we've added here to the reactant side, so we did that clearly. In both cases, the change in oxidation state corresponds to the number of electrons in the balanced half reaction, and that gives us confidence that the 2 half reactions are correctly balanced, and that means we can confidently move into step 5. In step 5, we want to multiply the 2 half reactions by factors that equalize the number of electrons. The least common multiple of 6 and 3 is 6, which means for our oxidation half reaction, we don't have to multiply it by anything. And for our reduction half reaction, we just need to multiply that by 2. To reiterate, we're going to be multiplying the reduction half reaction by a multiple of 2 so that the number of electrons in both the oxidation and reduction half reactions are equal to each other. So I'm just going to scroll down here and rewrite our oxidation and reduction half reactions, considering the factor that we multiplied our reduction half reaction by. And now you notice that we have 6 electrons in our oxidation half reaction, and we have 6 electrons in our reduction half reaction. In step 6, we want to go ahead and add these two half reactions. Keep in mind that if something appears on both the reactant and product side, it effectively cancels out. Ultimately, we get the following expression once we have added the two reactions. I want to point out the 6 electrons on the reactant and product side cancel out. 6 of these H pluses cancel out. We're left with just 2 on the reactant side. These 3 water molecules cancel out with 3 of these, and we're just left with 1 water molecule on the product side. Now, we have one extra step to do, and that's because we're dealing with a basic solution. If the redox reaction occurs in basic solution, we have to add enough hydroxide ions to both sides of the equation to convert H plus to water. In a basic solution, the concentration of H plus is not high enough for it to occur in the balanced equation. So this reaction actually has 2 H plus ions on the reactant side, which means we need to go ahead and add 2 hydroxide ions to both sides, right? We want it to be balanced. What we do to one side here, we have to do to the other in terms of adding hydroxide ions. Now here's something cool. H plus OH minus, this forms water. And in fact, since we have 2 of both, this forms 2 water molecules. Now we have 2 water molecules on the reactant side, 1 on the product side. We can go ahead and get rid of 1 of each. And what we're left with now is just 1 water molecule on the reactant side. Don't forget, we still have our 2 hydroxide ions on the product side. So what you see here is the balanced equation. We have our bromide ion plus 2 permanganate ions plus 1 water molecule. This gives rise to our bromate ion plus 2 manganese 4 oxide. All right, we have 2 of these manganese 4 oxides and 2 hydroxide ions. Before we say we are completely done, let's ask ourselves, is the charge on both sides of the reaction arrow the same? On the reactant side, we have -1, and we have 2 of these -1, so that's a total of -3 charge on the reactant side. And here we have -1 and 2 times -1. So this is -1, -2. This is a total of -3 on the product side as well. So the overall charge on the reactant side is the same as the overall charge on the product side. And this gives us confidence that we have correctly balanced this equation. And with that, we've completed everything we want for this chapter. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.